All right, section 9-3 is on rapid repeated integration by parts. The objective is to use a pattern to quickly integrate by parts. As you already saw in the first half of this section, you've learned the rapid repeated integration by parts technique. And that whole idea hinged on this fact that when you went through the first iteration of integration by parts, the results that you had for du and for v became the next choice that you made for the u and the dv. As long as that happened, we learned this nice little technique where we could eliminate stuff that we were writing down multiple times. However, that doesn't happen every time. The value that you end up with for du sometimes doesn't work as being the next choice for u. Or sometimes it's the case that what you ended up with for v is not the next choice for the dv. And so we're going to look at what happens if that's the case. We'll start out with an example here then. Example 3 there says to evaluate the integral of x cubed e to the x squared dx. Now I'm going to use this integration by parts technique on this problem here. And I want to make the exponential function, the e to the x squared, I want to make that the dv part. But if you're not sure exactly whether or not you can integrate e to the x squared, sometimes it helps if you find a derivative and see if that kind of gives you a little bit of a hint as to what you need in order to integrate it. And I'm going to do that here with this problem. So let's say that we have the derivative of e to the x squared. Now, again, I'm just worrying about the exponential function there. If you take the derivative of e to the x squared, you're going to end up with, it's a composite function, so follow chain rule, e to the x squared times a 2x times the derivative of the inside. Okay, so what that tells me is that, remember, every time you find a derivative, at the same time you found an antiderivative, that I could easily integrate e to the x squared as long as it has an x along with it. The constant, that's no big deal. I can deal with constants, no problem. But I really need an x in there. And this is what this process has shown me, is that if I were to integrate x times e to the x squared times dx, that I would end up with, in fact, if you want to put the 2 in here with it, you could. I'm just going to move it to the other side. If you integrate x times e to the x squared dx, you're going to end up with 1/2. The 2 is moving to the other side here. E to the x squared. Of course, there's a plus c when you do that. Okay, so as long as there's an x along with the e to the x squared, I can integrate it. So when we go to make our selection here for u and the dv, we're going to use this to help us do that. So I'm going to make u equal to, actually I should say, I'm going to make the dv equal to the x e to the x squared. Which if I take an x from the x cubed, that means I'm left with just an x squared here for u. So I've taken one of the x's from the x cubed and moved it over with the dv. All right, so let's take the derivative of x squared. That's the easy part. That's 2x. In fact, we actually just found the antiderivative of x e to the x squared. Turns out that was 1/2 e to the x squared. Now again, the problem that I run into at this point is the fact that if I'm going to use this rapid repeated integration by parts technique again, I have to be able to integrate what's in that dv column. And I can integrate it as long as it's got an x there. And I can look over here in the u column, and I see that there's a x sitting right there. If I could move that x over to the dv column, that would be really helpful. In fact, that's what our next step is. What we do is we draw a line here to indicate that there's no calculus that's going to take place between this last step and the next step we're writing down. You'll see why we draw that in just a second as well. But I'm going to just take the x and move him to the other side. So I have a 2 that's left in the u column. And I have 1/2 x e to the x squared. In fact, you can move anything you want from the u column to the dv column, or vice versa, from the dv column over to the u column. And to some extent, it would probably make sense to either move the 2 or the 1/2 so I can get rid of that constant. I'm going to leave it in here, but you certainly could move the 2 over to the right, or you can move the 1/2 over to the left. It wouldn't matter which way you move it. You can get rid of your constants. But I'm going to leave it as is. All right, now let's continue on with this rapid repeated integration by parts. Integrate the dv column, take the derivative of the u column. So derivative of 2, 0. Oh, those are nice. When we end up with 0, though, those are really nice in the u column. Over in the dv column, you're going to have the integral of x e to the x squared, again, is 1/2 of e to the x squared times the 1/2 I already have there is going to be 1/4 e to the x squared. And again, once you get a 0 in that bottom row there, you're done. So we again multiply this diagonal together. Now normally we'd say you'd multiply this diagonal right here. I'm going to go ahead and draw it in there initially, but we actually drew this horizontal line here to kind of illustrate that we didn't do any calculus from the or between those two steps. And that line that we have drawn in there, that horizontal line, is hopefully helping us see that we cross out that arrow. So this arrow right here that I just put in there, I'm going to get rid of because there was no calculus that took place there. That's what that line is helping me remember when I go to draw this out. So there's no line between those diagonals, so I jump down to the next two, and I'm going to multiply those, and then I got to integrate the bottom row, remember. And then you alternate signs, plus, minus, and plus. All right. So let's rewrite our original problem then. We had the integral of x cubed e to the x squared dx. Oops. That turns out to be equal to, our first diagonal there was x squared times 1/2 e to the x squared. I'll put the 1/2 out front, and then x squared e to the x squared. And then it's going to be minus, well, 1/4 times 2 is 1/2 times e to the x squared. And then finally, we integrate the last row, and the last row is the 0. Integral of 0 is our plus c. There's our answer there. That's a very fast way of getting that answer there. Again, if you didn't use the rapid repeated integration by parts, it would take you a little bit more time to write all that down. All right. Again, if you're going to just simply move stuff, that's what I've done here. I moved this over to here is what I'm really doing there. That's how the x shows up here. I draw that line to help me remember that. All right, let's take a look at another example here. Look at example 4. Example 4 says to evaluate the integral of natural log of x dx. If you've been wondering why we haven't learned the integral of natural log, or any log for that matter, it's because of the fact that it requires integration by parts. So we've waited till now to see that. We're going to go ahead and use the rapid repeated integration by parts technique, although it's only going to take one iteration, so you could choose to do it the other way if you wanted. But in the u column, I'm just going to make that equal to the natural log function, which means that what's left, there's nothing left there, so it's just a 1 that goes in the dv column. Remember, the product of these two has to give me the original function that I started with. Natural log of x times 1 is equal to natural log of x. All right, take the derivative of the u column, which is going to be 1 over x, derivative of natural log, and take the antiderivative of the dv column, antiderivative of 1 is x. And if you look at that last row, 1 over x times x, that's just 1. I can integrate that last row. Or for that matter, if you wanted to use that reassociation technique that we just learned, you could take and slide the x that's in the dv column over to the left and make that 1. Or you can slide the 1 over x over to the right and make that 1. Doesn't matter which way you do it, you get the same result. So there's several ways you could think about stopping at this point. But I'm going to stop right here because I can integrate that last row. So we add this first diagonal, we subtract that integral there at the bottom. So the integral of the natural log of x dx turns out to be equal to, it's the x times the natural log of x minus the integral of 1 over x times x. Again, that's just equal to 1 dx. And we have the x natural log of x. The antiderivative of 1 is just x. You have your plus c at the end, of course. So there's the antiderivative of natural log of x. It's x natural log of x minus x plus c. In fact, we'll just put that into a nice little form here for us. There's our rule then for the integral of natural log of x. In fact, you can use this technique then to integrate any log. Just do a change of base to get to natural log, and then use this rule to integrate it. So the integral of natural log of x dx is equal to x natural log of x minus x plus c. All right, that's as far as we're going in this section.